This is the lecture for Module 2 of Unit 8. This module introduces the crystal field theory for complex ions. Crystal field theory is a theory that describes the d electrons in the metal ion in a complex. So this theory applies for complexes in which the central cation is a transition state metal. And we'll have a number of d electrons. Right. The energies of the electron in the d orbitals of a metal cation are slightly changed by the lone pairs that are ligands. The result is complexes can be colored and can have magnetic properties different from the uncomplex metal. Right, let's begin by considering the d orbitals of the metal cation in an octahedral complex. Before a complex forms, all these d orbitals, as you know, have the same energy. This diagram represents increasing energy, but this picture is actually essentially a close-up of this. As complexation occurs, when we introduce the negative charges at a vertice of an octahedron, not necessarily ions, but maybe the lone pairs of electrons, you see that three d orbitals decrease in energy, and that two d orbitals increase in energy. The splitting in energy between these orbitals is called delta. And this orbital energy splitting pattern is characteristic of octahedral complexes of transition metals. This particular diagram then shows a stabilization of all the orbitals due to electrostatic attractions between the cations and the lone pairs. However, the energy separation between the orbitals, delta, remains. The diagram shows with the two orbitals that increase in energy and the three orbitals that decrease in energy upon the introduction of complexing ligands. It's straightforward to construct orbital diagrams for d electrons. For example, consider the titanium-3 cation, which has one d electron. Remember, when transition metals cations are formed, electrons are removed from the valence s orbital first. So, while the titanium atom has two d electrons, the titanium plus 3 cation has one d electron. You can show that d electron in the conventional way, pointing upward in spin. Put it in the lowest energy set of three orbitals, farthest to the left by convention. Although, of course, up or down or any one of the three would result in the same energy. Titanium-2 cations or vanadium-3 cations, for example, have two d electrons. Check yourself on the periodic table on that. Remember, valence s electrons come out first. The two electrons behave according to Hund's rule and fill up orbitals of the same energy one at a time. Same occurs for cations with 3 d electrons. Chromium-3, for example, has 3 d electrons. Here's an orbital diagram for the chromium-3 complex ion. Remember that this orbital spinning pattern is characteristic of complex ions. When you have 4 d electrons, however, or 5 d electrons, two possibilities appear. One is what you might anticipate from the odd processes learned in Gen Chem 1. When you have 3 electrons at an orbital of a certain energy, of the same energy, and 1 electron per orbital, introduction of a 4th electron causes, it results in pairing of 2 electrons. Similar to introducing 4 electrons to a set of p orbitals, as you saw in Gen Chem 1. Sometimes, in some complexes, however, this pairing does not occur. Instead, the next electron appears in the next higher energy set of orbitals, these 2 orbitals. This depends on the magnitude of the energy splitting between the 3 lower orbitals and the 2 higher orbitals. These quote-unquote low-spin complexes with fewer unpaired electrons occur in complexes with a fairly large delta. If delta is small enough, the repulsion energy of putting 2 electrons in one orbital is actually smaller than moving an electron occupying the next higher energy set of orbitals. So small values of delta give rise to quote-unquote high-spin complexes. There is, of course, no difference between high-spin and low-spin complexes if you have 3 d electrons, but in the event of 4 or 5 or 6 or 7 d electrons, there are different diagrams for high-spin and low-spin complexes. And this results in different numbers of 1 electrons. For example, a striking example, if there are 6 d electrons, low-spin complexes are diamagnetic, all electrons paired, whereas these complexes have unpaired electrons, or quote-unquote and we expect paramagnetic properties. High spin and low spin gave the same configurations when there are 8, 9, and 10 d electrons. Before you move on in this presentation, you should practice making high spin and low spin orbital diagrams for various cations appearing on this page. In the case of complexes, it's often fairly straightforward to determine the value of delta. Remember, delta is a relatively small difference in energy. It's the most straightforward example. Here we have a complex which absorbs light at 470 nanometers. Calculate delta for this complex. Alright, I think it's instructive at this point to consider what's going on. Light is getting absorbed at 470 nanometers. This is, in the case of this complex ion, corresponds to exciting an electron from the lower level of the d electrons here to the higher level. And this could be, we can imagine this occurring in this low spin or in this high spin case. We don't need to know which is which at this point. Now, this sort of numerical calculation is much like calculations involving radiation in Gen Chem 1. If you will remember, all radiation has a wavelength, which relates to a specific frequency, which relates to an energy of a photon, which is the light particle, radiation particle, which is getting absorbed by the cobalt cation in the process of moving the electron from downstairs to upstairs. Alright, so let's review this sort of math. Delta, the energy from the one set of orbitals to the other, is equal to h nu, energy of the photon. Nu, however, is c over lambda, because frequency times wavelength is the speed of light. You can show that this energy then is hc over lambda. You need to be careful with the units at this point, but you can then insert the value for h, 6.626 times 10 to the negative 34 joules times seconds from Gen Chem 1, multiplied by the speed of light, 3 times 10 to the 8th meters per second, and then divide this product quantity by 470 times 10 to the negative 9 meters, which of course is 4.70 times 10 to the negative 7 meters. You obtain an energy of 4.23 times 10 to the negative 19 joules. You may remember 10 to the negative 19 joules as being characteristic of the energy differences between orbitals and atoms that you calculated in Gen Chem 1. Let's give a bit of attention to the issue of complex ions and color. Because delta is relatively small, while the energies are relatively small, complex ions often absorb radiation in the visible spectrum, a range that people can see, as opposed to the higher energy UV absorptions that occur in, for example, in a hydrogen atom. 470 nanometers, I hope this picture shows, is blue light. Maybe you want to call it blue-green, shading cyan, perhaps shading down to that end of the spectrum. However, that does not mean the complex in this exercise would be blue in color. It's important to realize the principle of complementary colors in visible light. If it is blue, the complex is likely to be, or shading into green, the complex is likely to be orange, shading into red. The color wheel here in this diagram shows complementary color relations as well as approximate wavelengths of radiation corresponding to each color. Combinations of complementary colors look white, and if one complement of visible or white visible light is absorbed, the object absorbing that radiation will take on the complementary color. This principle appears in this exercise. Complex A, with a complex of cobalt made with ligand A is red in color, and a complex made with ligand B is green in color, which has the larger delta. Alright, as we've just seen from the color wheel, an object that is red absorbs green-blue light, and a green object absorbs red light. Complexes absorb light of a wavelength that corresponds to their delta. The smaller the wavelength, the greater the photon energy, and the greater delta is. As green light has shorter wavelengths than red, the object that absorbs green light, which is the red object, complex made with ligand A, is the one with the larger delta. We should consider at this point, since delta is important in determining the color of complexes and the number of unpaired electrons, and whether they are paramagnetic or diamagnetic, we should consider things that influence the value of delta. First, delta increases with the increasing charge of cations. So all other things, ligands, etc., being the same, an iron 2 complex will have a smaller delta than an iron 3 complex. Delta increases as the n-value of d orbitals, so complexes of silver have larger deltas than copper. Certain ligands produce a larger are known to produce a larger delta, all other things being the same. This is called the spectrochemical series. The spectrochemical series is shown here below. Cyanide, its carbonate, are quote-unquote strong field ligands producing large deltas. At the other end, weak field ligands, like the halogens, produce small deltas. It will not be necessary to memorize this series for this course, but you should be aware of it. For example, consider the iron complex of iron 2 with water versus cyanide. Note the difference in charge in these complexes, in spite of the fact they have the same cation. Which has the larger delta? We have two complexes formed from iron. The only difference is water versus the cyanide ligand. Cyanide produces a larger delta than water, according to the spectrochemical series. So the answer, which complex has the larger delta, is the iron cyanide complex. Here is an exercise. Explain why the cobalt ammonia complex is a diamagnetic low spin complex, while the cobalt fluoride complex is paramagnetic and high spin. Write orbital diagrams for both. As ammonia is higher in the spectrochemical series, it produces the larger delta, which causes the diamagnetic arrangement of electrons. This is readily illustrated. If you make orbital diagrams for both, you should attempt that before moving on. Here we have a diagram for the high spin or low delta complex. There are 6 d electrons in the cobalt cation, so we see each of the 5d electrons 5d orbitals gains an electron before pairing begins. This is due to the low value of delta between the upper and lower level of orbitals. Now there are 4 unpaired electrons in this species versus this high spin case, larger delta. All the electrons in the lower level pair before electrons begin to fill the upper level in this case. So we have 6 paired electrons or a diabatic electron configuration for this species. For ligands offers the possibility of forming either tetrahedral or square planar complexes. Tetrahedral complexes, and some pictures are shown, have tetrahedral shapes analogous to methane as seen in GenChem 1. The energy splitting for the d orbitals at tetrahedral complexes can be represented by this diagram. 2 orbitals are stabilized and are lower in energy than the d orbitals. 3 orbitals form a set higher in energy. The difference between these 2 and these 3 is always small for a tetrahedral complex. So small, in fact, it's rare for the delta for tetrahedral complexes to exceed the pairing energy. Usually, electrons will move up to the higher energy orbitals rather than pair. Because of this, most tetrahedral complexes are high spin complexes. Here's an illustration of a square planar complex, a copper ammonia complex, which has been discussed previously. Forms a complex which is blue in color, so we know it must be absorbing red light. The distribution of orbital energies for the d orbitals in a square complex has 3 orbitals that are lower in energy, a set of 2, and then 1 slightly above that. And then 2 orbitals that are higher in energy, 1 and then one higher than that. As delta is larger for second and third row transition metals, all four coordinate complexes of these metals are square planar. Electrons in these species tend to be paired rather than unpaired because the pairing energy is usually much less than delta. Square planar complexes are usually low spin. For example, nickel carbonate the nickel carbonate complex is diamagnetic. Is it square planar or tetrahedral? Write orbital diagrams for both possibilities. There are 8d electrons in nickel, so a square planar configuration would place 1, 2, 3, 4, 5, 6, 7, 8 into these orbitals, producing a diamagnetic arrangement. The tetrahedral low spin arrangement, high spin arrangement, on the other hand, that looks like this. Since this species with 8d electrons would be paramagnetic in a tetrahedral geometry, we know that its geometry must be square planar, which permits all electrons to be paired. This concludes the presentation on Module 2 of Unit 8.